And lesson 7 of structures and bonding, our last lesson on this subject, and really a summary to bring all the ideas together. And if you remember, everything we've done and all those rules, first of all we looked at the structure of an atom, and then this last topic, why do atoms react with each other, these atoms here on the periodic table? How do those atoms get happy? And the answer is they have a full outer shell. And everything for bonding is behind the full outer shell. And therefore everything behind chemistry is about getting a full outer shell and making new substances. So, to make a happy atom and get a full outer shell, where did we start? Well, we've ended up, never mind where we started, we've ended up with 4 types of bonding. So what I'd like you to do is turn your book sideways and either make your own table on a Google Doc or put this into your book like this. And what we're going to try and do this lesson is just go over and recap and bring the whole topic together in one place with all the key words and ideas, examples, and linking that type of bonding like ionic to the ionic structure. So pause and do this, and then we're ready to move on. Okay, so you've paused, you've done that. Make sure I've got a pen selected so I don't change slides. And this is where we started, so that first row. So ionic bonding, always between a metal from the left hand side of the periodic table, metal, and a non-metal. Always something that needs to lose electrons and something that needs to gain electrons. Always something that ends up becoming a positive ion because it lost electrons, and something that becomes a negative ion. And this is the example you worked through for yourself. So 2 electrons were transferred from the magnesium to the oxygen. Here they are, those 2 red ones. That gave that one a full shell and that one a full shell. This one lost 2 electrons. It became a +2, 2 more protons than electrons. This one gained 2 electrons, became a -2. A positive magnesium ion and a negative oxygen ion. Then attracted together, here, attracted because one's positive and one's negative, so we say that's an electrostatic attraction, causing strong bonds in all directions. And we moved on from that to look at the structure of this. So here, when we were talking about it, we were dealing with negative chlorine ions and positive sodium ions. The sodium's coloured purple here and the chlorine's coloured green for this diagram's purpose. And because of that, these attractions in all directions, here's one attracting there, there, there and there. I shouldn't draw lines really because those are covalent bonds, but those attractions in all directions, forwards and backwards. Then we had it that this builds into a giant crystal lattice. Now what I didn't say, and I should have said, was pause whenever you want to, and in your table, what are the key bits that are going to help you remember all of this detail at the very highest level, so that you haven't got a sort of ropey understanding of it, but it's really secure and you've got one place to go that sums it all up. So we've got a crystal lattice, and these molecules can be massive. It's a giant crystal lattice, and it's a solid, and it has a high melting point. And this was every time you have a non-metal and a metal. The metal becoming positive and the non-metal becoming negative. So you've got quite a lot on there. And then we actually went on and made sure that we understood and had all those in a sequence. So those strong electrostatic bonds in all directions, a giant crystal lattice, strong bonds that take lots of energy to break them, and therefore high melting points. And after that, there was a couple of properties. So being able to explain the high melting and boiling points because of those strong electrostatic attractions. And then if they're a liquid, the ions can move, and that means it can conduct electricity. So the ions can move when it's melted, so molten, or if it's soluble, when it's dissolved in water. And here, for example, there is a piece of salt, sodium chloride, and here's some little chlorine atoms, and here's some little sodiums, all mixed in with the blue water molecules, free to move. So what goes in here? Well, in this bit, hopefully you're going to be putting about, it has to be a non-metal and a metal. And the key ideas, well, you've got to have the word electrons are transferred between one atom and another, and you've got to have the fact that positive ions, negative ions, electrostatic would go in here, and then you'd have some examples. So you could go with sodium chloride. That was one of our main examples we looked at, and one of the main examples, this one loses 2 electrons, becomes oxygen -2. There you go. Magnesium oxide. And then structures and properties, and this is where you'd be putting in about your giant crystal lattice. And the properties: high melting point, doesn't conduct electricity. If you melt it, it conducts electricity, blah de blah. So there's quite a lot of detail to go in there, and that would have it all on one page, so you can go back and recap it again and again. After this, so stop and do that first, please, and then move on. After that, we moved on to covalent. And here we had an atom that wanted 1, and here's an atom that wanted 2. And they were both non-metals. So I'm just going to write non. They're both non-metals. And then we had the idea that, if I just draw the outside shell of the oxygen there, I've got, over here, I've got 1, 2, 3, 4, 5, 6 electrons. And here's hydrogen comes along and says, ooh, you can borrow one of mine, the only one I've got. And now all of a sudden oxygen's got 7. And another hydrogen comes along and says, and you can borrow one of mine. Now the hydrogens are now happy, they've got 2 each. And the oxygen is happy, it's got 8. So this type of sharing bonding, drawn out like a line showing where they're sharing a pair of electrons, a covalent bond. And we looked at different ways of drawing it. So this is the way I've just done, a dot and cross diagram, clearly showing which electrons originally belong to the oxygen with the dots, and the cross is there for the hydrogens. Structural formula like this that I just drew a minute ago. So those could go into your table as just an example. And then the structure, what's the structure like? And we said inside the molecule, so these are molecular, molecule, these F's go round as 2s because they've got 7 each, but now they've got 8 because they're sharing 1 each. This fluorine molecule has a strong bond inside it, the covalent bond, but then there's only weak attractions. So then we discussed the fact that these molecules, molecules are free to move. If the molecules are free to move, only goes to say it has to be a liquid or a gas, and most simple covalent substances are gases. So again, the atoms involved are both non-metals. Here we have sharing of electrons in pairs, covalent bond. Examples like O2, methane, CH4, water, H2O, no metals involved. And the structure, gases and liquids, low melting point, low boiling point, free to move. After that, we moved on to our third type of bonding. And again, it's covalent, But this time it's not simple molecules, these are called giant covalent. So instead of making small molecules, they make giant molecules. And the first one we dealt with was diamond, a giant covalent. And diamond had 4 bonds, bonded to 4 others. Very, 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 very hard. Very, very high melting point. High melting point, just like our ionic substances, but for different reasons. It's not ions attracting each other, they're covalent bonds, but lots of molecules joined together. And then we moved on to the other form of carbon, graphite. 3 bonds, layers, lubricant, free electrons. And here we had about the fact that graphite is the only solid non-metal that conducts electricity. And then we moved on to another couple of things, and we talked about the fact that diamond and graphite and graphene are all allotropes. So that's a key word, allotropes of carbon. And we said we had 4, maybe even 5, depending upon how we choose to classify the nanotubules. So graphene, single layer, very, very strong, brilliant at conducting electricity. How's that going to be when you've got several layers of it and lots of signs to come there? Put that inside other materials and it makes them load stronger, and it makes them able to conduct electricity. So you can use it as a composite. So use it as one of the bits in a composition of other materials. And then the Buckminster fullerenes, hollow circles, could be used to deliver medicines or drugs to different parts of the body. And then we move to the nanotubes. So all that strength of graphene, but in a cylinder, so even stronger. And using that inside materials to make them extremely strong, much stronger than steel, more bulletproof than Kevlar. And so now we're down to the giant covalent. So again, it's the non-metals. And we're talking about lots of bonds between molecules, mainly carbon or silicon, because they make 4 bonds each. And examples where you're going to put diamond and graphite and graphene and Buckminster fullerenes and nanotubules. The other one to mention is silicon dioxide, which forms giant molecules. Comes up quite often, worth having a mention. And the structure, giant covalent. Graphite conducts electricity, diamond doesn't. Graphite had 3 electrons, diamond doesn't, and a comparison there between the different allotropes of carbon. And lastly, we moved on to metallic bonding, where all the metal atoms want to lose electrons. They all want to lose electrons. So we end up with positive metal ions, and a sea of electrons. And that attraction between the positives and the negatives all holding itself together very strongly. Oh, find the right cursor. And then we went on to metal properties. Why do they have a high melting point? And it's those strong electrostatic attractions. Why are they malleable with the atoms sliding over each other? How can they conduct electricity? Because of the delocalized electrons. Why are they good conductors of heat? Because of the delocalized electrons. And this is all in your book, hopefully. And then we moved on to the fact that pure metals are a little bit soft. And by that we mean that they can bend easy and dent easy. And sometimes what we do is we make alloys. We mix metals together and we mix their properties. Iron can be a pure metal, and steel is a great example of an alloy. So down here with metallic, they're metal atoms only involved. Positive metal ions, free sea of electrons, delocalized electrons that are free to move, held together by electrostatic charges. Examples: iron, stainless steel, not on the periodic table, It's an alloy of iron and carbon and chromium. Iron, cheap, strong. Carbon makes the iron stronger, that makes it steel. Chromium, shiny, doesn't rust. Add that in and the iron and doesn't rust anymore. And then you've got your stainless steel, which is an alloy of those three things. Structure, giant metallic structure. Properties, high melting points, strong, malleable, conduct electricity, conduct heat. So your table should, by the end now, be complete. That table should contain all the highlights, and then you've got the detailed notes behind that to revise on as well. But hopefully that table's brought the whole topic together, and if there's any bits you're unsure of now, you know which bit you might need to go back and look over, and you've still got access to all the videos from this. Okay, thank you for listening, and next topic when we move on to quantitative chemistry, if you know all these rules now, and you've learned that and you understand the structures and bonding, the rest of chemistry now becomes a lot more straightforward. So make sure those are secure. Okay, thank you for listening.